Okay. Since I put topological order in the title of these lectures, I thought maybe I would start out with at least a slightly broader definition of these things before returning to the story that I started at the end of last time, which was non-abelian statistics. But the two go hand in hand. So condensed matter physics has a long and distinguished history, and one of the most fruitful notions. Do we, Filippo? Did I do that, or did that just come on? It was, went away. Oh, there we go. Okay, so it's okay. Yeah, that's right. I was being grandiose anyway. Right, so one of the most fruitful notions is this idea of an order parameter that I mentioned briefly when we were talking about icing. And, so an order parameter can be many things, but typically it's something like, so in icing, it's the probability that a given spin is, say, up. So probability meaning if you're in a classical system, you would just sum over all the configurations weighted by the Boltzmann weights. In a quantum model, this would be something like that, sandwiched in between the ground states. I mean, there's lots of things you can define. This goes back even further. You can ask a liquid gas and look near the critical point of liquid and gas and ask the difference in densities in the phases, for example, is an example of an order parameter. And, so from this stems the whole Landau theory of phase transitions and all this magnificent stuff. But in the sort of traditional way of doing things, of course, these order parameters are local. And then you can build this Landau theory and all that. But when the quantum Hall effect came along, so again, it's something I mentioned briefly, but I thought I'd do this more systematically now. So when the quantum Hall effect came along, this was very puzzling because you plot the conductance versus magnetic field, right? E squared over h, right? So you should never draw experimental graphs. Does this go up or down with magnetic field? It goes. Conductance goes down, right? Resistance goes up. This is being taped. I've forgotten the quantum Hall effect. Anyway, the conductance forms these plateaus, which I won't label. And and then there's a real honest-to-God phase transition. But the quote order parameter you might wish to use to describe these different phases. So these are quite obviously different phases. This is some new one. This is good. I can just go not tell you whether new one is greater than e squared over h or less than. Where new one and new two are integers, say. Let's just talk about the integer quantum Hall effect. But this isn't a local order parameter. There's no local order parameter to distinguish. Conductance isn't a local quantity. You talk about it between, say, two endpoints of the system, the conductance there. And so then people started to think, and so there was all this beautiful work in the 80s where they started to talk about non-local order parameters. And in fact, Frank mentioned one yesterday in the, this is not quantum Hall, in the AKLT chain. which is you want to ask in this so-called Haldane phase, which is the AKLT model that you all worked out the ground state wave function for, is in that so-called phase. And you might want to ask, well, what distinguishes that from some other phase? And the only thing is this non-local order parameter, the thing he wrote with the e to the pi SZs up there and so that's non-local. And so what emerged out of these pictures was a whole beautiful set of ideas that I'm giving very short shrift to. But one of them, and Zhao Ganwen being one of the key people who set these things out, was this idea of topological order. So it's inherently non-local. So these are systems where there's no local order parameter that distinguishes the phase, but there's some non-local one. And the one that's my favorite, just because it's very evocative of what's going on, is to count the number of ground states. So this is for a 2D system. Quantum system. Count the number of ground states on different genus surfaces. So no edge modes yet. So you put the system on a torus, you put the system on a sphere, if you can make a higher genus surface. And so this is hard for experimentalists to do, but theorists can have fun with things like this on the computer. At least do spheres and tori. And what you find is a remarkable thing is that the number of ground states, so we say it's topologically ordered. If the number of ground states, changes with genus. Initially, this sounds like a bizarre thing to think about, but when you think about it for a second, then you think, well, if it's an ordered phase, so our traditional definition of an ordered phase is, say liquid or gas. Well, if a system is a liquid, it shouldn't really matter whether I put it in a periodic, if I put it in a periodic world or not. If it's a gas, it's a gas. It's a liquid. That's something you can tell the difference between locally. Well, in some cases you can tell the difference between liquid and gas locally. But another example is the one that we've been doing is saying all spins lining up. So again, we're in 2D, and you've got a bunch of spins, saying a Heisenberg magnet, anti-ferro or ferro. They all line up again. Who cares whether I put periodic boundary conditions there? Who cares whether it's on a sphere or a torus? They all line up. Now, you might have to get it on some genus 7 surface. You might have to put a little defect in there, but still all the spins away from the defect will all line up. And on the other hand, if something is disordered, well, again, it doesn't care what genus surface on. It's disordered. They don't talk to each other. They don't line up. So this is intermediate. So topo order is intermediate between order and disorder in the following sense. Well, I say, if they're all lining up, they don't care what genus. And if they're not lining up, they don't care what genus. But if there's something non-local that affects them, they might very well know what genus they are, because there's only certain patterning if you want to think of spins. And that was one of the things that came up in the quantum Hall effect when people thought about Laughlin wave functions and their many generalizations. One of the characteristics you saw of those things is it really mattered. There were different ways of doing this on the torus, and these all corresponded to different ground states. And so, again, experimentally, I don't think you can do the quantum Hall effect on a torus. You would have to get the flux going around the middle, but still you can do this on the computer, and so you find this thing. So it's a very strange notion. So somehow the thing that's causing the system to line up knows what's going on at the boundaries. And then that leads again to this idea why edges are so important, because it does matter what's going on at the boundaries here. And so that's this notion. And so there's a lot to it. So I just wanted to give a very quick overview. So pause for any questions on that, since I've left out 99% of the field, but at least thought I would mention some brief things. Okay, so the setup shows that something funny happens at large distances. And one of the characteristics, so not a common characteristic. When I say characteristic, I don't mean every single system with topological order has it, but it's common. But non-abelian statistics that I described at the end of last time, at least all the physical examples of systems I know that have non-abelian statistics have topological order. I think it's pretty much required, although maybe I'm missing something, almost just by definition. So I'll even be bold and say this requires topological order. I think that's more of a definition than a profound statement. Anyway, these systems and so you might expect why, because so let me give just qualitatively an example I mentioned before, which is this P plus IP superconductor. So what Reed and Green pointed out, I guess about 15 years ago now, circa 2000 or 2001, I think 2000, they pointed out that, well, in a superconductor, you get vortices. So that's just a region where the order parameter of the superconductor, the phase of the order parameter of the superconductor, winds around as you go around a particular point. So you necessarily have a point where there's not a superconductor. The only way you can have something that wind around, where the phase winds around, is if at some point the order parameter is 0. So it's called a vortex, and that's where there is no superconductor in that small region. Outside the vortex, it's a superconductor. But one of the things, that's ancient story. But one of the things Reed and Green pointed out for these special P plus IP, so again, P plus IP means PX plus IPY. It's how the Cooper pairs pair, what the angular momentum is of a pair. And so if you have a vortex in the superconductor, you have a Majorana zero mode localized on the vortex. So just like we saw, so let me erase this, it's hard to read. Let's try this one. It's worse. Try these ones over here. Maybe not. So localized at each vortex is a Majorana zero mode, just like we described at the ends of the Ising / Kitaev chain. I should say at the end of the Kitaev chain. Okay, localized at each vortex. And again, so when I say Majorana zero mode, I mean it has this funny property that if I have two vortices, which you kind of need anyway, because if I'm going to wind something around one way, I have to wind it around the other way. I have to have them come in pairs, and I can move these pairs as far apart as I want, but then they form a quantum two-state system. So two vortices, again, if you're well below the gap, and so you're just looking at these states, so these two vortices form a quantum and if you remember, one of the key things I showed, well, I think I said it was key at the time, I showed in Ising, and it's similar if you do the Bogolubov-Dijen equations for the superconductor. They anti-commute. The vortex creation operators, just like for Ising, anti-commute. So if you change place, you pick up a minus sign, and that sounds very innocuous, but then what you have to do now to take into account, or one convenient way of thinking about it, again, you see this explicitly if you look at these Bogolubov-Dijen equations. I should just say what they are for people who don't know. These are just effective equations for superconductors. Superconductor is obviously a very complicated thing, but it turns out you can write down these simple equations to describe the physics of the superconductor extremely well, called Bogolubov-Dijen equations. These are just equations for free fermions with like these C-dagger terms. Anyway, so in order to implement this, what you see in the Bogolubov-Dijen equation is it's the best way to think about it is attach a string to these vortices. And so if I then bring one around there, well then when just your rule is when you cross the string, you pick up a minus sign. And for those of you in the Ising model, familiar with the Ising model, this is what happens when you write down the fermions. This Jordan-Wigner transformation I wrote down. Actually, well, you're all familiar with the Ising model since I told you so quite a bit about it. Okay. So, anyway, so the situation there is very similar. In fact, it's basically identical, at least for the things that we're interested in, identical to the Ising model. And so you can think of then our vortex creation operators in Ising as having these strings as well. So I'll write that down explicitly in a minute. But see, now you start to emerge where the non-abelian statistics are going to come from. Okay, because, all right, so we got, remember I said for non-abelian statistics, so what happens, to remind you what I said at the end of last time, we have some ground state wave function. So in this case, so someone pointed out this doesn't have to be ground states, and indeed, but now I'm going to talk about ground states today. All right, labeled by some label. Okay, so that's just the labels the ground state. Okay, so in this particular case, we may have many vortices. So that's just the label. So, well, again, I'll write it down very explicitly for the things, but let me just remind you schematically what's going on. Well, then when you say you just have two particles, or two grounds, location of these two zero modes. Didn't leave myself enough room here, sorry. So when you interchange the two, if you do it slowly enough, adiabatically, so that you don't excite things above the gap, so you're just looking at the stuff at the on the ground state, well then at least in principle, you can change ground states. I'm going to show explicitly in the next few minutes how you can do this in the Ising thing. But so now, okay, so first, before we do that, let me just say, well now look, we're starting to get the ingredients to do this. Okay, so first of all, we've got degenerate ground states. So there we go. So by ground state, I mean in the presence of the two vortices, I should say. So there's a ground state that exists in the presence of 2 or 12 or how many vortices you have. So what I mean by that is you make those vortices, these regions without superconductor, they're not going to go anywhere. That's stable because of the topological winding of the order parameter around those points. As long as I don't put in a lot of energy and I keep these very far apart so they don't annihilate, that's what I'm calling a ground state. Okay, so I've got this ingredient, the degeneracy. So that's one ingredient. But then also I've got this sign. that says that no matter how far apart, I take this guy around that guy and I pick up a sign in the wave function. So I'll call this non-locality. You can affect the wave function even very far apart. So and that's what statistics is. You change the wave function around, you never move them close together. That's why I said before, remember in 1D, in strictly 1D things, you can't really have statistics because I can't make them interact without moving them through each other and I have to deal with interactions. In this 2D setup, I can move this one way, way far away. The string goes off. Anyway, so same there. So now this is only a minus sign. This just means they're fermions. So that doesn't sound too dramatic yet. But the catch is now, but notice we've got this two-state system, which is a little more to the thing. So if we keep putting vortices in, we get bigger and bigger systems, and we have lots of things we can do. And so we can get this, and that's what I'm going to show next. But any questions about the rough idea first? Okay, so now let's go. I put this there to make sure that that's why what I'm about to show you really is exactly the same notion as this. There's just a little trick to do braiding in one dimension, even though I just claimed you can't really braid in one dimension, but then the trick is you can. Okay, so let's first imagine now taking some 1D system, okay, and then we've got our superconductor up here, but through some very complicated experimental wizardry, which can actually be done, what I can do is I can tune the coupling between the superconductor up here and my quantum wire running along here. So I trap electrons running along here. I've got a superconductor up there, very low temperature, so we're well below the gap. And because experimentalists are so clever, they can tune the interaction between the superconductor and there. Or they can just cut off the superconductor. So let's say schematically, let's just put the superconductor there. All right, so in this region, then there's some induced interaction of the Cooper pairing type in the wire along here, but there's not here because I don't have a superconductor there. All right? So then what happens is in here, I get my, quote, Ising / Kitaev chain. Let's call it Kitaev. Right? Because we have an induced CC plus C dagger piece. But now here I don't. I don't have a superconductor over here. So I get my edge modes. And so to use the Ising language, this would be like an H less than J region. But then out here, I have H greater than J. But of course, I can do this again. Put my superconductor here. And I get two more zero modes at the end of there in this region where I tune H less than J. So this is obviously difficult for experimentalists to do, but this is entirely conceivable, and that's what people are starting to do right now. Okay? So now, okay, but the catch is, so remember, on each of these, if we're looking at the ground states, again, the gap is enormous. We're working at very low temperatures, so we can just ignore everything above the gap. Well, so here has a two-state, there's a ground state is a two-state system. The system I called plus and minus. So there's two ground states, plus and minus. But of course, I can make this pretty far away. These guys don't really talk to each other. So here again, I have two more ground states, plus and minus, and so forth and so on. So the point is now, so then I can label these zero modes psi 1, psi 2. Remember that was my labeling before, but these are now new ones, psi 3, psi 4, keep going. So these Majorana zero modes always come in pairs, so I have, say, two, what should I call the number of zero modes? Usually people call it n, I guess I'll call them n. So 2n zero modes. But I have a 2 to the n dimensional right, because for each sort of Ising/Kitaev chain, I get two zero modes, but then I just get a two-state system, right? So there's n Ising chains and Kitaev chains with open boundary conditions. Okay, is that clear? So I'm just going to label, it's a Hilbert space. I can label it in many ways, but I'll just label this in the obvious way. Let me just call it, I forget what So what I'll call the state for each, I'll just label it by this Z2 quantum number. Right, so where this so that's my space 2 to the n dimensional, and I can choose plus or minus sign for each of those, and that's my 2 to the n dimensional, the basis, these are the basis states for this. Okay. So again, I'm going really slow because I want to convince you that I'm not pulling anything fancy here. We showed all that really explicitly and gruesomely. Just put a few more words here to say you could do this. Okay. All right. Well, so now, okay, so say I wanted to interchange psi 1 and psi 2. Well, I obviously can't do that without having things interact, and that violates my rule, self-imposed rule. I want to do statistics, so I have to keep everything far apart. But then, very clever observation of Alessia et al., I don't know, 5 years ago now, 2010, I think, 6 years ago. But still, you can do this in quasi-1D by just introducing what they call a T-junction. Other people call Y-junctions. But anyway, I'll draw it as a T. So if I have now, I make my wires, and I put them in a T. So those are my wires. That's easily done. They do that all the time. And now remember, for the experimentalists, we have another dimension. You can put things on top, right? So it's not so crazy to imagine, doing that sort of thing there. And so the point is to say let me do the order I want to do. So say now, I can put my superconductor down here if I have a T-junction. So I can make this So the clever idea is this. Okay, so let's just look at one. We'll look at more than one in a minute. But let's just look at one here. So I have my thing here, but then my wire, my one-dimensional wire where I've trapped electrons to run along there, has this junction here. Well, so now it's easy to interchange psi 1 and psi 2 without ever having the ends come close to each other. Remember, very important, we showed that this was all localized. Well, you can almost guess what I'm going to do here. Well, so now by tuning your superconductor, and again, this can actually be done, you can then shrink the size of this region if you want. So let me draw this. Let me use some color and draw it bigger here. In fact, let's erase all this. And then I put a wire there. Well, by tuning, at least in principle, let the experimentalists work hard to figure out how to actually do it, but I can tune the region here. And so I can make now, let's try to make my superconducting region shrink, or at least the coupling to the wire shrink, and so I can move that thing like that, just by sliding it down. Do it very slowly, make this still really far away, so this thing has no idea what's going on. All right, but now I can couple my superconductor in along this wire if I want. These theorists can do it. So I can move that up there. So the end is now there. I just make it go that way instead of that way. That's why if you want to think of it as a Y junction, then all three legs are sort of equal footing. We'll draw it as a T. Upside down Y. Upside down T. All right? Well, see, now you see what we can do. Now we can move this guy. So push that guy way up there. So now we can move this guy along. So let me label all these. That's 1, 2, those psi 1 and psi 2. Well, I'll write that once, then I'll just write 1 and 2. So that's psi 1 and psi 2. So that's 1 and 2. Still 1 and 2. Okay. Well, you see where this is going. I can move that there, but then, of course, I can just keep moving this along down here. So it'll look like this. So that's one. That's 2. That's 1. All right, well, now it's kind of obvious what I'm going to do. I can bring that one down, and then I've exchanged them. So this was my initial thing. Sorry, I ran out of room there, but then finally, well, I'll do one more intermediate step. I move that one back down, but now it's 2, and then 1 there, and then finally, oops, wrong color. Now I got there. And the key thing is I've interchanged them, but without ever bringing the two together. And again, we showed in fermionic language these are localized, and so they're far apart from each other. Yeah. Yeah, but it's not, but yeah, but you'll see when I introduce multiple ones, So yes, if I just, all I cared about this, but all this is going to give me is a minus sign. So that would be the world's most complicated way of getting a minus sign in a wave function. The point is I'm going to make a network of these things, and then I can just do individuals. So that would be corresponding, yeah, in principle I could just rotate an individual region, but of course experimentally you can't do that. Right. So if this were the only thing I was interested in doing, you're absolutely right. You could just rotate the two, slowly rotate the two around each other. Good. Any other questions? Yeah. Well, no, so, right, so it's a little subtle here, but the way you should think about that is each of them, so like I do with the vortices, you take each string and have it to infinity. So first of all, I should say, first of all, if you do this carefully, you'll see you get the minus sign for one, but just in words, you can see what's happening. Okay, so this, nothing's going on there, but sort of think of this string going off. And so the key part when I get the minus sign is when I drag this guy through there. So if you really think of the two guys having individual strings, but one can terminate on the other because yeah, so you don't have to do it that way, but that's the easiest way to visualize it. And so what happens when I bring this one across here, I'm bringing it across the other string. This way. Yeah, that's an important subtlety. But I say, the other thing is, I mean, look, these are operators we can just define, the adiabatic transport of these operators, and you see there's no way. The point is, you can put the minus sign in various places. You can move the strings around, but the point is, ultimately, you pick up that minus sign. Good. Any more questions? Yeah. This quarter. Yeah. That's then, I would call that an experimental detail. So you have, well, no, but it's very important. Remember, everything is robust, right? And so the point is, you do have to worry about, I mean, not to dismiss it, that's something, there's parameters there that you would have to worry about, because now when you're right at that point, you've got, the thing could move off in the other direction. But if you imagine, God, so what the experimentalists are sort of God, they're tuning all these couplings. Let's imagine in this perfect experimental world, they can tune all these couplings however they like. And then the key thing, remember, everything's robust. So if one coupling is a little bit off, that's not going to screw everything up. We'll take H much, much less than J. So if one of H is a little bit errant and all that. But see, so then what they have to do is, tune all these ones to H greater than J. But as long as they can do that, and we'll trust them they can do that. But yeah, that's a real issue. Yeah, people study. In fact, that's the world of Y junction. You look at papers. There are all these papers over the years, long before all this was interesting. People were interested in this question. Discuss, well, what happens when you put three quantum wires together? You can get like modes that live just on the junction there, and all that story. And there's actually a whole long, interesting story there. So, and one could then, if you want, try and bring that story into this story and ask, well, can I get some interesting physics there? But we're going to just pretend that we can tune it, which, experimentalists are God, they can tune it, so none of that physics matters. And it's just a fair question. Good. Yeah. No, so then there would be, yeah, so then that's a precise example of what I just said. Then you can't have an odd number of them, so something would have to be living at the junction. So that's like, yeah, so that's the exact situation. If you did that, which of course, at least in principle, you could experimentally do, then you would have to worry about the physics of the junction. So absolutely, that, both. First, and that might be very interesting. I'm sure I know people have worried about that. I'm trying to think of it in this particular context. I can't remember, but very possibly. Good. Any other ones? All right, good. So this is now the world's most complicated way, like I said, of getting a fermion minus sign in the world, right? But we do have now we've physically moved them apart, so the wave function of the system will pick up a minus sign. So I guess the net thing, this was the starting point, and then this was the final point, so just use a different color there. That's what we did. We went all the way around, and then net just went from there to there. Okay, and so then the wave function, hope at least It's reasonably plausible, and if you do this more carefully, you see that the wave function will pick up a minus sign. So if x1 and x2 are the locations of the two zero modes, we now have minus psi x2, x1 in wave function language. But now let's ask what happened to our ground states. And in particular, let's do this now in a second quantized formulation. And think about what we've done now. Well, what we've sent is, if you follow this around, right, so let's see, so we moved 2 up, went up there, then we dragged 1 through, and so what we've done, start with psi 1, well, psi 1 has gone to minus psi 2, because with psi 1 goes to psi 2, but when we dragged it across there, we put the minus sign there. You can take different conventions and move that minus sign around, but always what you're going to get is one of them will get mapped to the other, and the other one gets mapped, well, they change roles, but one of them picks up the minus sign. It's obvious the minus sign has to be somewhere, because we know that psi 2, psi 1 equals minus psi 1, psi 2. But we've done a little bit more in our operation. We've done that. Okay? And so this is a unitary. So that's a statement about operators. And so we can write a unitary matrix, which I'll call U12. So a unitary matrix U12, which does this. And so in particular, what I mean by that is U12, psi 1, U12 dagger equals minus psi 2, and U12 psi 2, U12 dagger equals psi 1. And sorry, I changed the. Okay. And write down the answer, I guess. Well, I didn't think of any. Well, maybe I'll think of another homework problem. The only homework problem I thought of was a really trivial one, to check that the matrix U12 equals 1 over square root of 2, 1 plus psi 1, psi 2. Does that. So I guess homework check that. That's like 2 lines, so not too demanding a homework assignment. Okay? All right. So that, I say, the world's most complicated way of getting a fermion minus sign. But now we start to think, well, if I put a bunch of these together, can I start to do these things? And so I'm only going to pick up a minus sign individually, but minus signs are part of matrices, and well, you'll see how it goes. So what let's leave that one. What do I leave? Let's erase this one. Okay, so let's now take the situation that looks like this. So I put I make my wires look like that, and we'll make that 1 and 2. It's very important that I use the same color, but then I also have 2 wires, but I connect them by my T-junction. So then I have another wire with another region. So certainly a mathematically consistent thought experiment, and let the experimentalists figure out how to do it. Actually, they are figuring out. They're starting to do these things. Okay, so I've got 3 and 4, and it's very important to use the same color. This is all one, they're all fermions, this is all one system, but what I did, remember, in the Ising language, this one is tuned H less than J. Along there, it'll be H greater than J, and H less than J there. So now, again, we can play these games. So I could just exchange 1 and 2. It's exactly the same as what I did before I moved that. But now we can do something more exciting. We can interchange, which one did I work out? 1 and 3, I think, or 2 and 3? 2 and 3. So let me go through that to make it clear. And then so I don't have to write this again. What I'm about to show you is that I can do something that does this. And let me get my conventions straight. I think I might have done it so the way I did it puts the minus sign there. So, and I guess I got to, now write a U23. And I'll show you the steps, but this is the answer. Okay. Oh, that's a 2. Any other typos? All right, so it's not hard. So, okay, so I want to interchange 2 and 3. So, let's see, I wrote out the steps carefully so I won't be stupid. All right, so now I can drag this guy down. So I move that guy over. Well, I'll erase all this. So, be a little bit quicker. So I can drag this one along here and then bring it down. So again, I bring that down there. So in fact, this is the situation someone just asked about. So if I bring them down, so that's all superconducting, but I do this carefully, I do have something living at that junction there. Right, so literally all I do is exactly what I did before, and then change that gradually to H less than J. If I do this there, still I have that 0 mode. Do this everything slowly. So, oops, sorry, there's no X here anymore. You can see. I mean, how is this? Well, so imagine. Okay, so remember, there's not along this wire of the string, there's nothing much going on with the string. That's the bulk of the system, right? In the spin language, everything is lined up, okay? Yeah, of course. Well, okay, so remember, so what this, all this is notation for is H less than J, right? And so I can imagine just gradually tuning as I go along, tuning regions of H less than J and H greater than J. Flicking this. Yeah. Right. Right. That's right. Have all. Yeah. But this is by. Okay. Well, so let me draw the next step, and then maybe that will look. So then, okay, of course, that's there. But so then what happens here now is I can start moving it along there. So all these guys are just sitting there. Oops. Sorry, let me just do it. And again, let me label these. This is still 1, 3, 2, 4. So much crap. All right, so let's. And so now, so if I move, sure which way I want to move. Yeah, I want to move 3 here. So I'll move, so let me just draw this first. 1, 3, 2, 4. Okay, so that, we're not doing anything here, that will go there. Well, see, this has to sort of terminate there, and then this has to terminate there. So again, I think the better way to think about it is, this question was asked before. Think of all these, remember, all the zero mode is a string of spin flips in the Ising language, okay? And in the fermionic language, it's not even there. This is just letting us keep track of, when we bring something around. These things aren't there. They can be moved around wherever they want if you think the full two-dimensional picture. It's just a way of remembering that these two things don't anticipate. It's a branch cut. Maybe the right word is branch cut. You can move it wherever you want to move it. And so what it's just saying is, so this is a little bit ambiguous, I agree. But so, of course, up to here, it's completely non-ambiguous. There, it's completely non-ambiguous. So just think about that. And so it's just basically saying, well, that's why we just let us keep track. That's where we're going to put the minus sign. And there's no invariant notion of where we put the minus sign. Just know if you go all the way there, there has to be a minus sign at the end of the day. So I think that's maybe the best way to say it. Yeah, so don't think, so in the fermionic language, remember, these strings aren't real. They're just artifacts of the way we choose to write out the theory of it. These are just fermions we're moving around, and these are just regions we're taking h less than j and h minus j. Yeah, right. So again, so imagine you would write down some lattice model, and that's what the studies of these Y junctions said. Remember, in the Ising language, it's all just beautifully clear. This is why I like the spin language so much. You're just writing down a bunch of states. And it just tells you that there would be two states sort of associated with this. If you did the three, if you put all three together, you would find two degenerate states affiliated. Well, this one, you would find 4 degenerate states. And you could think of this, the difference between the two would be localized. Well, 2 of the states would be localized at this point. An operator that would toggle between the 2 states would be localized at that point in spin language, in fermionic language. Localized in fermionic language. In the spin language, you would have to include that string. But that's all. Yeah, exactly. So if you could write out every single bit of this very completely explicitly in the language I used, in this lattice model language. And you would just find that this whole thing is a 4-state, there's 4 ground states to this thing, and when I move this around, there's still 4 ground states. I mean, that doesn't change. It just looks a little funny in these pictures. Okay, good. Any other questions? These are important. But yeah, I'm not doing anything particularly fancy. Okay, so now you can see where this is going. So I move that there, and so now I can move 2 just happily up there. Nothing's in the way of that, so we went from that to that, and then we can bring 2 all the way up. Where's my thing? So, right, so we'll have 4 and then 2 by bringing 2 up there, and then, well, 1 and 3 will still be there, but then of course I could just drag 3 along, and I've done what I claimed I can do, is interchange 2 and 3. So we'll take a break in a minute, but let me just finish this. Oops, these are green. So where we've got 1, 3, 2, 4. Okay, so I did this. And again, never were any of the edge modes ever close to each other. These Majorana zero modes, never did they come close to each other. They can make this big enough, they can be arbitrarily far apart. But I've interchanged the 2. And so again, this sounds like the world's most complicated way of interchanging. Well, what I wrote before, this sends psi 3 to minus psi 2. And the whole issue is right there when we crossed the string due to the other, and psi 2 to minus psi 3. Sorry, to plus psi 3 over all minus psi. And so then you can define a matrix U2, 3 that does this exactly like we did before, which is just 1 plus psi 3 psi 2. But it is easy to check, and we'll work out the details after the break. Those two matrices do not commute. And that's where the non-abelian statistics come, because all these matrices do is move you around in our four-dimensional space of ground states. Everything stays really far apart. The quote excitations, the Majorana zero modes. But it's not going to happen. And so I'll work that out explicitly, and you'll see that at break. Okay, so 10 minutes or so. It used to be 6 weeks, and so by week 5, nobody ever wanted to set foot in the room. So this is only week 2. Okay, good. So let me say a little bit more. Okay, so people were rightly sort of bothered by this little jump there. But the important thing to remember, for the fermions, the string is an artifact. It's just keeping track if I want to write down where I jump. And in the vortex language, what happens is you have this phase, but this phase 5 or 2 appears. And so you have to worry about, where you're going to make phi jump by pi. But that's just an artifact of how you choose to write the problem. And so to illustrate this, I realized another way we could do this. So remember, the whole point is these things are identical. Right, these Majorana zero modes. So in this situation, I have the same system. So say I had drawn my strings like this, right? If you could have other quasi-particles over here, or I could just have put my thing and then connected these two, 10 miles away, and then reconnected these two. It doesn't matter. So if I had drawn it this way, my strings this way, which is a perfectly consistent thing to do, well then you never have that situation people were unhappy with where all 3 strings meet at a junction, or are you? Well, so what happens, I bring 3 down like that, and then bring 2 up, and then just bring 2 back again. So it's just kind of crossing the string with no vortex out there. So you can see, I won't draw all those out. So that one might make you happier, because it's no different from what we did before. On the other hand, you can then think about for a second, it's really no different from that either. It's just bringing this vortex across the string. If there were 2 zero modes here, then you would have to worry what happens when 2 zero modes come together. But that's then interacting, and that violates the whole point of what we're trying to do, which is we're keeping them far apart precisely so we don't have to worry about the interactions. Okay, good. Any more questions about that, or have I at least convinced you? I haven't pulled anything too fast on this. Okay, so what we showed now, let's erase all these pictures. And if you do this with superconducting vortices and a P plus IP superconductor, then you don't have any of these worries, and the math is exactly the same. And in that context, what I'm about to show you is an observation of Ivanov's. I think shortly after the Reed-Green paper, Ivanov made this beautiful observation that that these things don't commute, and thus you now have non-abelian statistics. But let's just be pedantic here, and we'll just show explicitly that they don't commute. U1, 2, U2, 3, well, if I just multiply them out, I get 1/2, 1 plus psi 1, psi 2, plus psi 3, psi 2, and then you get minus psi 1, psi 3. Right? Remember, the minus sign comes because psi 2 squares to 1, but I have to commute it through when I multiply this by this. That's a 3 there. You have to commute it through the 3 so that the 2's can annihilate. So that picks up a minus sign. But if you do U23, U12, well, these pieces are all the same. 1 plus that, but then you get this times this, and you get minus psi 3, psi 1. But psi 1 and psi 3 anti-commute as well, so that's not pi, sorry. That was the same as above. So you got that, but these two, so these are not equal. So now let's think about what this means acting on my actual space of ground states. Well, remember, when we just had the one system, we showed that psi 1 acting on plus gave you minus, and then likewise, of course, vice versa, because it squares to 1. Oops. And then psi 2 can't do the same thing. It does interchange them, but our conventions, I think, were that. Minus I plus. All right. They have to do something different because remember, psi 1 and psi 2 anti-commute, so they can't do the same thing. So they both interchange. They toggle between the same two ground states, but in our convention, psi 2 multiplies it by that. And so then U12 plus minus just gives me plus or minus I plus minus. Okay? Because that just acts on the single two-state system. But now when I've introduced 3 and 4, well, I've got two two-state systems, so I've got a 4-state system. So U23 will have to act on the system, well, minus 1 F1 minus 2 F2, because this is the 1-2 system, and this is the 3-4 system. Okay. So I'll leave, this will be a homework exercise then. This takes slightly less trivial than the other system. You see, this is not diagonal, and it kind of can't be because, again, it doesn't commute with U12. So what you get is, in fact, well, again, check my signs, but what I got was 1 over square root of 2 minus 1 F1 minus 1 F2. So you get that back again, but then I get minus I times minus 1 F1 times minus 1 F1. So this state, notice crucial the minus sign. So it flips this state. So if this were plus plus, so for example, then plus plus would go to 1 over square root of 2 plus 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 minus minus. Oh, sorry, minus. There's an I and So if I did it right, that's what you can check on the homework, if I got the sign right. But the crucial thing, and it's pretty obvious it has to, if they're not going to commute, it doesn't just give the state. So this is exactly what I was talking about with non-abelian statistics. You've got some state. They're all far, the zero modes are far apart. I do this manipulation. Well, boom. You go back to a state that's completely equivalent. I've got the wires, I've got the zero modes are all in exactly the same places that they were. I did just these manipulations by changing H and J around, and I get back a new state at the end. It's still a ground state, right? We've got this four-dimensional Hilbert space, but I've moved it around. And likewise, you can work out for the homework. It's pretty obvious. You can check that U23, U34 doesn't commute with U34, U23. That one's so painfully obvious. He just changed labels in what I wrote down before. Okay, so that's just stunning. Even if there were no potential applications for this in the real world, I think that's just absolutely the most stunning thing. These things are very conceivable making. You can very conceivably make these things. They've already, I think I mentioned, there's already pretty strong evidence that these wires do exist and these zero modes do exist. And you can look just on the archive about a month ago, there's a paper, 11 authors starting with Asen and ending with Alicia. It's not in alphabetical order. Sets out kind of a roadmap, if you wish, sort of what are the things to do next. And so, well, I'll say about a few of these things, you know, how do you experimentally go through all the steps you need to finally get to this? Any question? Yeah.
So what is the here, can it precisely predict these coefficients? Because of course we have degenerate ground states and you move around.
Yeah.
And you will end up with some state.
That's right. Well, no, of course not. I mean, we went to a lot of work to show that we change state. Yeah, so this is not arbitrary. Those coefficients are fixed solely by these general notions. The fact that fermions anti-commute, if you wish. This solely depends on the fact that fermions anti-commute, and that these are Majorana. I should say fermions anti-commute and that they're Majorana. That's all that went into this. There's no ambiguity whatsoever, other than maybe I screwed up a sign. But with the correct answer, which everyone will check on the homework that I got the right sign, is that's it, period. There's no other, you do this manipulation, you get that. There's another manipulation that'll probably give you a plus sign there, but that's it. Well, so the goal is to, well, do this, right? And yeah, so that's what there's these now literally hundreds, probably we're in thousands of papers now written on first how to actually do this, and second, then say you could do this, how would you see it? And that's why I mentioned this paper that's kind of this roadmap is, okay, so now we think we've got these wires, then making two of them should be no big deal, all right? The next step, how do we physically manipulate this? And but more, of course, more importantly, how do we observe this? I mean, that's a major question. How do you actually see this? But actually things like ground state degeneracies and all that, you know, you can probe this via lots of things. They have lots of probes in there. And so that's actually probably better. So in fact, in some ways, observing this sort of thing is much easier than I mentioned before with observing just abelian fractional statistics, you know, where you go around and get a phase. Phases are really, really hard to measure. But this is, you know, just that's taking one state and, you know, just moving it around and asking what phase does it pick up. That's really hard. This state and that state are qualitatively very different. And so you hope you can design an apparatus. It's at least conceptually much easier to design things that do that. The drawback is, of course, getting this behavior is much more difficult to get. But once you got it, at least you can think of a lot of ways to try and see that. You know, people have tried to see these kind of things in quantum Hall systems, but quantum Hall systems are just so inherently difficult that. But there are reasonable claims of having seen things like this, just not unambiguous, unfortunately. Good. So if they can do this, then they'll really have observed these. It's the remarkable properties of Majorana. So this seems so innocuous, but it's this fact that there's these two delocalized things, but that have the same two-state system. That's really the secret. And where topology comes in is again these strings and all this story. That's what's protecting this. So the emphasis, this is not some arbitrary sign. So let me write down my answer to Slava's words about my Slava's question. This is, to use a word I used before, this is robust. Meaning, remember I made a point of saying those zero modes still existed even if I changed some of the H's. As long as I don't make the system gapless, it's all still there. And this behavior required none of the details of the system. So this linear combination is completely independent of the details of the system. And like I said, I think this is a magnificent achievement, even if there were no application. But the application that people want to do these things with, so let me mumble a few words about this just to give you an idea. The application, the killer app, is to build a topological quantum computer. So if you think of this now, it's a four-state system, but by doing these manipulations, at least within this, I can't get all four states, because it won't change overall fermion number just within this thing here. But I can think of this as a two-state quantum system. I have plus plus and minus minus, and at least I have one unitary operation I can take to this linear combination by acting with U23. So it only takes it to a particular linear combination, but it does take it to a linear combination. And topology protects both all these things I've talked about for 3.5 lectures. So the topology, to be somewhat crude here, so topology protects the ground state degeneracy up to these exponentially small corrections, which are completely negligible as long as I can make these wires long enough. And also protects the operation, the U23. So the operation I do, so if I think of this as a qubit now, so this is a two-state quantum system, it doesn't require changing fermions. So the point is these have the same fermion parity. So I don't have to inject fermions. If I just took the two ends of one wire, I'd have to inject a fermion to move between the states. But these two I don't have to. So all the architectures that people are thinking about using these things, think of this at least as your basic qubit, those two states. So now we would just have to have a bunch of them. A bunch of four-state systems, we kind of ignore half of them, and then we get two-state systems. And then we can do operations. And of course, if I can manipulate this qubit like this, but then I have U4, 5, and I can just, at least in principle, do all these things. So I can make a whole network of these things. You can make a big network this way, or we can just make a network this way and interchange them this way, or if you want to I make a whole array of them. So let's, do something like that. And at least imagine doing these things and doing all these manipulations. And that's what a quantum computer is. You've got quantum two-state systems, and you have a way of manipulating the two-state systems. And what's nice here is, again, that phase in there is the phase I think there is always I or minus I, depending on which whether I guess I could use U23 or I could use 2-3 dagger, so that would be interchanging them in the other order, things like that. So that's your quantum computer. So that's what you want to do in a quantum system. Then you can do prime factorization for very large numbers and crack RSA. Allegedly, there's an algorithm that shows, everybody probably knows this by now. There's you go to a website with HTTPS, and so it's secure. It uses this algorithm called RSA that relies on the fact that it's really, really hard to factor large numbers into their prime factors. And there's an algorithm called Shor's algorithm that shows that you could factor large numbers in polynomial time if you had a quantum computer. Long way about that, they've only factored, I don't know. Someone told me they went up to 45 or something now, but that's been factored. I forget, it was 34, I don't remember. But anyway, so it's a long way off, so you don't have to worry about your credit card number being stolen, at least not from that. But yeah, so I'm trying to think, is there any other lore? So that's the idea. And the topology. Oh yeah, one other thing I should say here. The one catch is, though, if say you could do this would be, like I say, just a stunning achievement. But this is not, so this is robust. But the problem is this Majorana quantum computer. Same if you manage to make and manipulate vortices in a P plus IP superconductor. Again, P plus IP superconductors almost certainly exist, but it's pretty hard to do anything with them, and because it's not even, I think, fully established that they do exist, although the evidence is pretty good. So Majorana quantum computer is not universal, and what that means to be able to do Shor's algorithm in order to factor large numbers, to prime factor large numbers, you need to do lots of different kinds of unitary operations. And I made a big point of saying, my operation is protected. That's a good thing. That's a feature, right? Because if you don't know precisely what you're doing in a quantum computer, if random little phases are coming in, well, then it messes up everything. Coherence is lost. Everything gets messed up. So that's a feature. But the problem with it, we can only do that one manipulation. We can do, obviously, U34, U37, whatever. But you can show rigorously that you cannot get all unitary operations on this Hilbert space. So that's what universal means. So you just can't make all unitary matrices by this exchange. Like I say, that's just a mathematical fact. You can just prove that you can't get everything. So it's not universal, so you couldn't do everything. So you can prove that if you're allowed one thing, one sort of operation on your quantum computer that's not topologically protected, you can choose one, there's some particular operation you can add to this, then you can make it universal. So then you can do anything by putting these topologically protected ones with your one non-topologically protected one. But it's not quite universal. As a result, you may have heard the word Fibonacci going around. And this is a long story again. So if you could make a Fibonacci quantum computer, then you could do it. So let me just say very schematically, ask questions at the discussion section today if you want me to explain this in more detail. What the difference is, well, in Majorana, you put two Majoranas in the Majorana system, you put two Majoranas together, form a two-state quantum system. That's something I've belabored, I said about 1 million times. And in fact, something Slava wrote down at one point, and for those of you familiar with conformal field theory, this is called the fusion rule. And Slavin wrote this down at one point, and Ising, who wrote the non-chiral version of it, So for those of you who know conformal field theory, this is obvious. If you don't, well, just bear with me. Think of that as a Majorana. You fuse it with another Majorana, well, you get a two-state system, and I'll label the two states by 1 and psi. Psi's a fermion, and remember our two states, one of them had one fermion prior to the other, had the other, so we label them like that. So in a Fibonacci system, however, there's one kind of particle, like the Majorana, but you fuse them together, and so you can fuse them together and you can get kind of a trivial system. But then you fuse them together and you have this bizarre situation where you get back something that's equivalent to what you originally had. So there's no Z2 symmetry. So for example, the Z2 symmetry here would be phi to minus phi. So that's what preserves that. There's no Z2 symmetry there. And if you know what Fibonacci is, that's a generating sequence for the Fibonacci numbers, right? So anyway, so that's a little bit vague, but the point is there, when you do rotations of Fibonacci operators, you'll get phases you get enough phases and you keep doing this, you don't just come back to yourself again, and so you can then represent any unitary. So again, ask me more in the discussion section. You want me to say a little bit more about that? All right, that was a pretty brief, but I hope not completely worthless introduction to what a topological quantum computer is and why the reason why so many people are working on this. I don't think you even need this as a motivation. I think it's just so amazing, even without it. But this then makes it even richer, the things you can think about. So you can think about now, given the system, what kind of computations would I do if I had 1,000 qubits like this? And so there's an entire field of quantum information that's basically about that question. Any questions? Okay, good. So let me say a few. Okay, so let me not shift gears, but so something I've said many times, it's still written up there, that this is robust. But when I said robust before, as long as fermions were free. So robust so far. Okay, but now the question is, well, let's add some fermions. Now, whether you're a condensed matter physicist or a particle physicist, you know, at least in one dimension where we've been working, you can add a term with 4 fermions in it, put some indices on them, and that can be marginal. In higher dimensions, things are much better. In higher dimensions, a 4 Fermi operator is always irrelevant, so you can safely ignore it. But here it can be marginal, and there's models called the Luttinger model in the condensed matter world, or the Tiering, or the Gross-Neveu model. Probably some of these have come up with earlier speakers that describe what happens. And the fermion interactions change the physics dramatically. So an important question is, well, is all this magnificence that I talked about, mess this up? Well, so one obvious thing is, so if I bring 2 chains closer together, so I always very carefully, when I drew those networks, I kept them far apart, so then probably everything I said is good. But what happens if I have my 2 wires and I've got my 2 zero modes at both ends, and what happens if I bring them close together, just physically close together? Well, of course, these guys now can talk to each other and interact, and there's an easy answer. If I do that, and I do nothing to restrict that, that will gap out the edge modes. It's easy to show. And that's kind of obvious because I said, remember, if you take a periodic system, you don't have this degeneracy. That's easy to show. There's no zero mode. Remember, there was the gap between the thing and nothing in the middle when I looked at the epsilon k's. So I can obviously, if I connect that one to that one and that one to that one, I make a periodic system, so I lose the edge modes. So that's pretty obvious. It's not stable, so that says if I do that, well, I better keep those. I better keep them apart, or do something else. So there's a famous pair of papers by Fidkowski and Kitaev who impose a symmetry to forbid this from happening. And so what they said, let's impose time reversal symmetry in this BD versus D versus what SPT. This is relevant. So they impose time reversal symmetry, which in fermionic language, or Majorana-fermionic language, is really easy to do. And so what you can then do is impose the time reversal symmetry. So psi 2j will go to psi 2j, but psi 2j minus 1 goes to minus psi 2j minus 1. And if you remember, all the terms in the Hamiltonian were of the form psi 2j minus 1 times I. So one of them picks up that doesn't pick up a minus sign, that picks up a minus sign. But time reversal is anti-unitary, which means if you've got complex coefficients, you complex conjugate them. So this is that. Right, so that Hamiltonian, the Kitaev Hamiltonian, is that, but it puts a restriction that you can only couple odd to even odd and even in one term. So odd terms, so psi 2j, psi 2k are forbidden by the symmetry. And so then you see right away, well, remember this was psi 1, and that was psi 1, we'll call that chain 1, chain 2, we'll call that 3, I guess, in my other notation. Well, that's the index, and so this would be forbidden. So you can't have that if it's time reversal invariant. And then this is this class BD1. And so then they proved a remarkable result, though, which is, I'm not going to go through it, I'll just tell you what the answer is. They proved that if you, so if in this case, the symmetry is not just Z2, the symmetry is Z, because I have for lots of chains. So the topological invariant is Z, because I can have lots of chains. So this is again why getting too worried about what classes it's in is maybe not so important. If you just make 10 chains, well, you're in the same symmetry class, but obviously the physics of 10 chains is very different from the physics of one chain. So don't get hung up on what class you're in. Worry about whether you have 10 chains or one chain. But if I have a bunch of chains, then you can have lots of these invariants. But of course, now I couple them together. And I can't couple them together like this because I've forbidden it by symmetry, but I can add a 4 Fermi term. And so basically what they show is something really funny, at least to me, is that in fact, you cannot couple an arbitrary number of chains together and expect that you have this thing for this invariant for every single chain. In fact, it's broken down to Z8. So this says if I have one chain, it's fine. I've got my Z2 quantum number. If I have 2 chains, I'm good. I have 3 chains, 4 chains, fine. I can couple up to 7 chains, but when I couple to 8 chains, via some kind of 4 Fermi term, I can then continuously deform to the trivial phase. So by trivial, topologically trivial, meaning like h greater than j, without ever closing the gap. You can always get rid of it by closing the gap, but if I go to the other side. But without closing the gap, just by adding 4 Fermi interactions. And those who like field theory, there's a nice way of seeing this by using Gross-Neveu models, and why it's 8, because the O8 Gross-Neveu model has some special properties, is the way you see it there. So it's very cute. And in fact, so in the first paper they showed that, in the second paper they showed, in fact, this classification, the 1 through 7, those were all topologically distinct from each other as well. And the 8 is not a coincidence. You know, there's 8-fold way, and it's all very beautiful mathematically. So you have to impose that symmetry, though. If you don't impose time reversal symmetry, then this doesn't mean anything. Any questions? Just wanted to say that briefly. No, for the whole system. For the whole system. Well, you can do whatever you want. This is a stronger statement than just coupling edgements. You can couple anything you want. In fact, you can even do this with periodic boundary conditions. Remember, I showed there's a way to get the topological invariance even in periodic boundary conditions. This was just sort of a cartoon to explain what's going on. So you can put any boundary. The statement of topological order doesn't depend on edge modes, right? No, I'm saying, right, but now I'm saying you can't. So what their result says, you can consider bulk interaction terms, and this still survives up to the 8. So you can allow any interaction, any 4 Fermi interaction you want, and these will still preserve. So this is an even stronger result than our earlier one. Oh, it says, yeah, so this is stronger, but it just says it's not perfect. If you have 8 of them, you can get rid of the whole thing. So, and if we're really going to make one of these networks, we have to make sure that they're far enough apart so that they don't interact and mess this up. But yeah, I'd be happy with 1 wire at this point. I don't need 8. But good. Any other questions? Okay, good. So last, any other things I want to say? Yeah, good. In the last 10 minutes, then I can plug up, say a little bit more about something I've been doing recently, and that Jack, who's sitting out there, has been working on too. So it's what happens now to the edge 0 mode with interactions. Okay, so Fitkovsky and Kitaev's result shows that at least, say, I couple 2 chains together, would say that the topological order survives. So that means that now I'm going to introduce some new language, a weak edge 0 mode survives. And what I mean by that is that there's a 0 mode that so there's an operator that takes you from one ground state to another exists. So if we look at the whole spectrum of our model, so we have our spectrum in the -1 to the f equals 1 sector, and then -1 to the f equals -1 sector. So there's some operator that says these two are only split by some exponentially small number. But Fitkovsky and Kitaev's result doesn't say anything about what happens up here, even for a 1 particle state. So that survives, great. So that's what their result is. So that's a good sign, topological order, and that's maybe the most important one. But one thing I pointed out briefly, and I'll say again, is the existence of this operator psi which obeys, remember it was H psi equals well, 2 epsilon k in general, but remember this one was just something exponentially small, and that psi squared equals 1. Well, and psi 1 anticommutes with minus 1 to the f. So you take these three conditions together, and what that says is, so not only is there an operator, the psi toggles between the two ground states, but psi has to toggle between any of the two states. So it says that the entire spectrum in both sectors is the same. And this isn't at all obviously true. Just because you have a symmetry, you know, a Z2 symmetry, says nothing about whether this, when you diagonal, something commutes with Hamilton, you diagonal. There's absolutely no reason in general why the spectrum in the two sectors is the same. And in fact, in Ising, if you go for H greater than J, you have two sectors. The Z2 symmetry is still perfectly good, not even spontaneously broken. But you don't have anything like that. Just plot on the computer. So it's important to think, just because there's a symmetry, it means, what the symmetry means is I can look at this sector and I can look at that sector, but it doesn't say anything about what happens. So this is a much, much larger statement. And so there's been a lot of stuff in the recent literature, which is not orthogonal to people thinking about topological, but a different line of development that goes under the name of many-body localization. So that's another story. Again, I can explain what those words mean a little bit in the discussion section if you want to hear about it. But one of the things people doing many-body localization has motivated is for people to think hard about what's going on at the top end of the spectrum. And so then there's all these interesting questions, things called the eigenstate thermalization hypothesis, and all sorts of interesting stuff governing what's going on way up high, not just the ground state that usually we're paying attention to when we're doing physics, but way up high. And so, in fact, there's even a paper, a couple papers, one by, let's see, Hood Altman, Eshvan, and there's two more, I'm sorry, Bari, I forget the one more author whose name I could forget, sorry, who even mumble something about, well, you know, if this is true, you could even have a finite temperature qubit, right? Because this operator works even if you're a very high temperature, even it's not, you don't have to just deal with the ground states. You could maybe just do this even at very excited states, maybe. Mumble. But at least it starts to be very provocative. And so, and in fact, so then the question is, so now what happens? So this would be robust. I showed that thing is robust. I can change the H sub i's. But what I didn't show, because I didn't talk about it till now, is what happens with interaction. So you can ask now this question, what happens to this thing? So Fitkovsky and Kitaev only show that these two remain degenerate. What happens up there? And so the answer is kind of interesting. So in general, if you add some interaction, even an irrelevant one, because we're asking what happens way up here. So we have to get out of this mindset of field theory where you ignore any irrelevant interaction. You just throw out and say, who cares? It's not matter. Well, it does matter for up here. It does matter for way up in the spectrum. So the relevance and irrelevance is talking about the low energy, and the field theory in general is typically only describing the low energy states of the theory. So that doesn't answer anything. So what? Well, this is a subject that's very much under discussion. But what I showed, and maybe next time I'll say a little bit more about it, maybe not. But what I showed in one particular example, which is the XYZ spin chain. So again, if I say more, this next slide will define this precisely. So it's another spin chain that generalizes Ising. If you work that out there and you can fermionize it, so this corresponds to two Majorana chains. Yeah, you ducked a homework problem because I could have made you show this in the homework, but I don't have enough time to write out this in detail. Maybe I will next time. So two Majorana chains coupled by a 4 Fermi interaction. Well, maybe that'll be my final. Do I have to have Filippo, do I need a final? Wasn't I supposed to give a final to my, the people who are being graded this? Do I need do I have to give a final exam to the people? Oh, maybe this will be the final exam. Okay, this is good. Anyway, to show this, that it's not that hard. You take the XYZ chain, it's a spin chain on two-state systems just like Majorana. It's easy to see that, it takes a little work, but not that hard to see that it's two Majorana chains coupled by 4 Fermi interactions. So this paper I wrote recently, that maybe or maybe not I'll discuss next time, shows that, in fact, this strong zero mode, the thing I just erased, still survives. So well, this is the strong zero mode, and it survives. So you have this exact degeneracy for the entire spectrum up to something exponentially small, because these things don't quite commute. And you can show psi squared is 1 and all that. So maybe I'll say a few more words about that. So the moral of mentioning this is the story of what's going on is still very much in flux. Okay, see you. All right, questions I should ask. I've talked a lot. Yeah. Yeah, that's the question. Well, Jack is, yeah. So, yeah, I don't think I'm ready to say anything in public. Certainly, it's the reason that I could show it to be true is due to the special nature of XYZ, because it's integrable. That's why it worked. And so what we've been working through now is other examples, and I don't think we have any conclusive moral yet. That's something we're trying very hard to understand. There even seem to be sort of intermediate things in between strong and weak. So the stories. So there's definitely more. So one thing I'm comfortable saying in public. There's definitely more. It's not just a fluke of one particular case. There's definitely some more structure there, and there's probably even gradations in between strong and weak that we're trying to get. But yeah. So that's well. This part's written up. Yeah. So it may be a fluke and maybe not. But I think it's pretty remarkable that the structure. I mean, there's just still more to the story. Yeah. It's the many-body spectrum. Many-body spectrum. So this is the entire, just like for Ising, this is the entire spectrum of the theory, right? And these are I mean, you can think of it as a fermion theory, but this is a strongly interacting fermion theory. I mean, you can tune this 4 fermion interaction as high as you want, and you'll see these things. Yeah. Yeah. Oh, so all I said there, okay, so the question they're trying to answer is just take a bunch of Majorana chains, one way of phrasing what they're doing, take a bunch of Majorana chains, couple them together via 4 Fermi term. See, because in their language, if you have just a single, first thing to say, which I didn't say, so if you take a single Majorana chain and try and add a 4 Fermi term to that, then that's irrelevant. You can easily see, because you have to spread it over four things, so it turns out it's a dimension 4 operator, so it's very irrelevant. Because Fikovsky and Kitaev are only talking about the ground and low line states, so they say, all right, well, that one doesn't even count, so we're done with that. You don't even need time reversal symmetry. That one is just flat out. Okay, but now we take 2 chains. That simple argument I gave says clearly that'll gap out. I impose time reversal symmetry now. So the only thing I can add that couples the 2 chains now, won't couple, the simplest thing I can add would be a 4 Fermi term. And then their statement is, no, that does not. You still have the 0 modes. So that's their statement. But theirs is only about that only the ground state degeneracy, which for the applications I gave, that's all you need. So from the point of view of topological order, this thing about the Ising model is very much that's something else. And so in fact, one more word I should say. So the transition, so if I take H, this is true for H less than J in Ising. But if I do H greater than J, the 2 grounds, well, there's not even 2 ground states. So those aren't degenerate, right? So those will be whatever. And then you look here and, I mean, if it's really remarkable to look at, I mean, they don't look anything like each other. I mean, you think there's a lot of eigenstates, how can I tell? But, I mean, if you go to, very big system, find you plot them and it'll just look black because, there's so many things. But if you do any finite size, reasonable finite size, they're still split and they look totally different. So this is what people have named an eigenstate phase transition. So when H goes, so this is H greater than J. So again, these two spectra are completely different. And so usually in condensed matter physics, or in all physics, when we talk about phase transition, we're talking about the ground state. But here there's an eigenstate phase transition. There's this qualitative difference between the entire spectrum above and below. And that's not that's not obvious also. Again, if people often say this is dual to that, but I don't, if you look at the whole spectrum, they're just completely different spectra in the two sectors. So I don't, dual is the wrong word for what goes on in the Ising model. All right, sorry, long answer to the question. Yeah.
So your criteria for strong zero mode is clear, but so what do I have to do to get the weak zero mode?
Well, that's simpler because so strong zero mode would be unique. I mean, you just need some operator basically that takes the two back and forth, and so psi1 and psi2 are examples of them. But they're not unique. I could multiply psi1 by any power of the Hamiltonian itself. Actually, that would still satisfy this. So any operator, you could take any operator that just took that to that and did whatever it wanted to any other of these states. Yeah. Right. So it's just the ground state that would do it. So I mean, those weak zero modes are still very interesting because those are the things that we would be using to manipulate our qubits. But if you're asking this bigger question, yeah, you need this other operator. Yeah, I better stop because it's so get Frank to talk. Okay, thank you.